Welcome back. In this lecture, we are going to look at the applications of some of the analysis that we have developed so far in the course. Recall that we started these series of lectures by proving the fundamental theorem of algebra, which is looking for solutions to polynomials, right? Algebraic equations. And that is how we were led into complex analysis and right now we have developed enough theory to actually venture into differential equations. In this lecture we are going to show at least this is the first part of that lecture in which we are going to deal with differential equations. In the next lecture we will show the existence results. So in this lecture we are going to make this connection between how the solutions of differential equations can be seen as a consequence, as fixed points of some operators and so on. Okay, so let's start with the kth order ODE. Okay, and this is a nonlinear ODE, so it's an ODE of this form where the kth derivative can be separated out and the rest is all up to k minus 1 derivatives and the independent variable. So f is a function of k variables, right? F is a function of k variables here and the non-linearities of this form. So this f can be non-linear in all its arguments here. So it's kth order because the highest order derivative is k here. This is an ordinary differential equation. Okay, so this is a kth order differential equation. It is the first observation we would like to make is that any kth order ordinary differential equation can be reduced to a system of first order ordinary differential equations. So how do we do that? What we do is that for each k from 1 to k, we introduce the new variable ui, which is the I minus 1 derivative of y. Okay, and with this, then you introduce this vector u, which has these components u1 to uk. So what is u1? u1 is y1 minus 1, which is 0, which is y itself. So u1 is y itself, u2 is y prime, and so on. Okay, so uk is yk minus 1, which is here. So this is u1, u2, and so on up to uk. So you have k elements here. So this function f here can be written as fx comma this vector u. Okay, with this new integration. So in this ODE, if you notice, x is the independent variable, y is the unknown. So we have to solve for y in this differential equation. So we are rewriting the unknown in terms of another unknown, which is uy. Okay, now these are vectors. So we have k vectors corresponding to the k minus 1 derivatives of y. Now we introduce, so this system becomes u prime of fx comma y, right? By the way we have defined, this vector is u, so this is fx comma u, right? And here you have yk. So now yk is precisely the yk can be written as the k minus 1, that is uk prime, right? That's how you can write it. So what is the system of equation here? So u is a vector, this vector. So u prime is the derivative of each individual component here. So you have k elements here, and this is all the derivatives of u1 here. So u1 prime, u2 prime, u3 prime up to uk prime. Okay, now what is u1? What is u1 prime? u1 prime is this. So you have u1 here. u1 is yi minus 1. So u1 prime is, so u1 so u1 prime is f, and so the first component here is f1. So f1 is u2. Okay, so f1 is u2. So u1 prime is u2, right? Which is true because u1 prime is, if you differentiate this one, you get yi. Yi is u2. if you take this to be u1, so this is y, so this is u1 prime is y prime, and y prime, the way we have defined, is u2. So right, similarly, so if you differentiate here, you add one more derivative here, that is precisely ui plus 1, right? So ui prime is ui plus 1 from this equation. So you have we have that this is equal to, so the first component f1 is ui plus 1 and so on up to k minus 1, and the kth term fk is this component here. So this equation now, that is what we are doing is this equation and this equation here, right? So both these together is going to give us a k system of first order ODEs. So what we have done here is we have reduced a kth order ODE to a first order system of ODEs. Okay. So if we can solve for u here, then we can solve. Then since we know u, we know all y. So we know y. We just have to solve for u1 here. So if we solve for u here, u1 is the y that we want. So we have solved for this scalar kth order ODE as well. Therefore, any question regarding existence and uniqueness for the kth order ODE can be reduced to the existence and uniqueness questions of a first order system of ODE, which basically means that we really don't have to worry about studying every kth order ODE. If we understand first order system of ODE, I mean their existence and so on, if we answer these questions for first order system of ODE, we would have answered it for any kth order ODE as well of this form, right? Okay, so now let's look at how do we solve. So let's take the uh, simple case when you have I mean, we are going to do it for kth order system of ODE. Let's just for simplicity look at the scalar case where you have only one equation, right? So you have, if u is a solution to the first order ODE of this form with the initial value prescribed at x naught. X naught is an element in a comma b. Okay, and u is a solution in some interval of the domain I. So u satisfies this differential equation in the interval I, and I is an interval which contains x naught, and the value of x naught and the value of u at x naught is prescribed. So if u satisfies this, that means the graph of u is will lie in the strip I cross minus infinity comma infinity, right? And this graph will pass through the point x naught comma u naught. U naught is the value u takes at x naught, right? So we are looking for the unknown u, that is the unknown curve which lies in this strip I cross. If it satisfies an I, it lies in this strip, right? So we are looking for a u or a curve in this region which is passing through x naught comma u naught and satisfies this equation. So the way we want to interpret the solution is, suppose this u that we are looking for is bounded, right? If it's a bounded curve, then it's actually lying in a rectangle of the strip, right? Because it's bounded curve. Suppose the curve, I mean the u we are looking for is bounded, then this curve is actually lying in a rectangular region, not just a strip. It's a rectangular region contained in the strip because it's bounded above, below. So you get two horizontal lines. So it's inside a rectangle. So if we assume that this function f, which we have here, which is defined as a function of x and u, right? So if we assume that this function f is continuous on the closure of the rectangle that we have seen here, and if that function f is integrable, that is Riemann integrable in this, because you see you have u prime here. If I integrate both sides, I get the value of u, right? So that's the, if we can do that, then that's then we are done, right? So for that, this function has to be integrable. So that's why I'm just motivating uh, whatever we are going to do later. So suppose your function was a bounded, then then it is, so the graph of the solution is contained in a rectangle, and if the given function, this f is given to you, if this f is given in such a way that it's continuous and on the closure of the rectangle, and it's Riemann integrable, right? Mm, it's Riemann integral because it's a bounded function in a on a closed set, right? So it's a Riemann integrable function. So if it's integrable, then you can integrate both sides. So you get, if you integrate both sides, you get integral over x naught to x u prime of integral over f x naught to x, right? You get this if I integrate both sides, right? And this x naught is the value of u that is given to, right? We are given the value of u at x naught, so we are trying to do this integration from x naught to x, from that starting point or the initial point where the value of u is given. It's usually not necessarily initial point, right? It could be a midpoint, I mean, point in between also. So it's called the initial value, in the sense that the value there is known. Okay, one data point where we know the value. So if everything is nice in these integrals, so this is integral of derivative, so this is ux minus u naught, and this is, and we have, and if this is integrable, this is just some value, right? This is integral over f, integral of f, which means what we have obtained is the solution that we want to obtain in a very nice situation where f is integrable and everything. The solution of that ODE, which we said, which is 9.1, okay, this ODE is 9. So the solution of this ODE is given by this formula, right? But the only point of this formula depends on u again. So this is like a recursive thing. So the value of u is given by this formula, right? So we really cannot solve it here because this formula involves the unknown u as well here. Okay, but this gives an idea how the solution looks like, right? So this is where the main idea comes. So what we have done is that we have written our differential equation in an integral equation form, right? This is an equation. So here again, in the earlier form, we wanted to solve for u, which was in a kind of equation which involved derivatives. Now we have a unknown u in an equation which involves integral. So we have converted a differential equation into an integral equation. As life becomes simpler, we will see, right? The idea is, I mean, we are doing this because it kind of becomes simpler in this case. So the only issue with this formula here could be that when you say is f of t u t, that means this t comma ut should be in the domain of f for this should be valid, right? So the only thing that can go wrong here is that if u is such that u goes outside the domain of f, then this f is not defined there, and then things can go wrong, right? So this is something that can happen, right? And in that case, you don't, I mean, you have the integral is not well defined, even the function f is not well defined, and so on. So these things can happen. These are issues I'm pointing out because we did this under some assumption that f was continuous, it was integrable, this, that, and so on. So to avoid this kind of difficulties, what we do is that we assume that this f is defined in a comma b cross minus infinity. That is, we are including the entire all possible values, so that you don't have this issue that u is such that it goes outside the domain of f. So f is defined in the entire strip a comma b. So x is coming from a comma b, the domain of u, so that is fine. And then it's f is defined everywhere. Okay, so we are not restricting f just to the range of u. Okay, because a priori we don't know u. So since we don't know u, we don't know the range of u. So if we don't know the range of u, based on which, because the domain of f depends on the range of u here, right? So we just say that f is defined everywhere. That's what we are saying here to avoid such issues. of not being well defined and so on. So what we have is, and we now have an integral equation of u. Now, if you observe very carefully, whatever we had here in the right hand side here, this which involved, because u naught is given to us, x naught is given to us, f is given to us, t is some values between x naught to whatever x that we take. So use the unknown here. So if this actually defines an operator on the space of continuous functions. So if I take I to be the interval a comma b, say the closure of the interval a comma b, right? But here I'm just taking a comma b, later we will close it. So I can think of this operator. So I take any function, continuous function, and the image of that function u under t is defined like this, whatever the right hand side of that integral equation was. So tu, so tu is defined as this thing, which means that in this equation I can replace the right hand side by tu, the operator t acting on u. So this equation becomes u equal to tu. Now what does u equal to tu means, right? So now tu, so once I take a u, this tu is again a map from I to r, and it will be a continuous map and so on. Okay, the way whatever assumption we have made, right? And see, and if we take I closure, then make it closed set, that is compact set, then the space of all continuous functions is given by the supremum metric. We have seen all these things before, and which induces the metric, submetric, and so on, the supremum norm, right? So this operator now makes the integral equation as u equal to tu, which means the u that we are looking for is precisely the fixed point of the operator t, right? Because this is u equal to tu. So solving for u here is basically trying to find the fixed point of the operator t, whether t is defined this way. So finding the fixed point of this operator is the solution to this problem. And that fixed point is, and that operator is from the space of continuous functions. So what I want to point out here is that suppose you have a u, which is a continuous function, which is a fixed point of the operator, right, of this operator. It's a fixed point operator, then u by definition is actually once differentiable, that is, it's continuously differentiable. Okay, and then because it's a fixed point, which means u satisfies this formula, right? And it becomes, and you can differentiate it, and you see that is valid here, right? Because u satisfies this formula, you can differentiate it. So u is c1, and it satisfies the ODE. Okay, because that equation was obtained from the ODE, so it will satisfy the ODE. Conversely, if you have a solution to the ODE, okay, we have seen from whatever we discussed in here, it will be also a solution to this fixed point problem. So basically what we have seen is that we started with an ODE, first order ODE, and we said the solution of the ODE is same as the fixed point of some corresponding operator on the space of continuous functions. So finding the solution is same as finding the fixed point of the operator. So can we find fixed points of operators? So one fundamental result that we know about fixed point, which you all must have seen in your course on metric spaces, is the contraction mapping theorem, right? So what is a contraction map? So if you have a metric space with a metric t, and if you have a map from x to x, we say it is set to, we say this map is contraction if you have a scalar which is between 0 and 1, 1 not included. Okay, if then, and this condition is called the contractive condition. Okay, that is alpha can be 0 but strictly less than 1. So the distance between the image of points is smaller than alpha times the distance between the point, and this happens for all x and y in x. If such a thing happens, then you say the map is a contraction. If this happens for the choice when alpha equal to 1, then you call the map is non-expansive. Okay, and if the alpha and if this alpha is something that is between 0 and infinity, then this is actually the Lifshitz continuity. So contraction is a special case of Lifshitz continuity, right? When alpha is less than 1. So as an exercise, you can show that every contraction operator is Lifshitz, which is clear here from definition, and every Lifshitz map is continuous. This is also easy. You should be knowing, because if something is Lifshitz, it satisfies this condition, and from here actually continuity follows. Okay, once you have contraction maps, then you have this contraction mapping theorem, which tells you about the existence and uniqueness of a fixed point. So if you have a map, contraction map from the metric, from a complete metric space to the same to itself, then there is a unique fixed point of f, right? That is, there is an x in x such that f of x is equal to x. So let's quickly do this proof. It's an easy proof. Most of you must have seen this proof before in your metric space, in your real analysis course or so on, when you did your metric spaces, and most of you must have even enjoyed this proof and liked the proof, and must even remember the proof. So just for completeness, let me just do it here. So the idea to get the fixed point is that you start with any point, arbitrary point x0 in x, then you sequentially define the subsequent points. So you look at x0, look at the image of x0 under f, call that x1, look at the image of x1 under f, call that x2, and so on. So xn plus 1 is defined as the image of xn for all n. So you have a sequence of points in x. So we first show that the sequence of points is actually a Cauchy sequence. So to show Cauchy sequence, we look at the distance between two consecutive points in the sequence, xn, xn plus 1. By definition, xn is the image of xn minus 1, xn plus 1 is an image of f of xn, right? So this is equal to this. Now, but f is a contraction map, so there is an alpha such that this condition is satisfied, alpha. Now you apply the same thing, xn minus 1 and xn is image of f of xn minus 2 and f of xn minus 1. So you use the same condition and then again use the contraction, you get alpha square d thing. Keep on doing this. Finally, it will stop at the stage where some alpha power n d x0 comma xn. This is how it will come, right? So this is what we have. So to prove Cauchy sequence, we start with any 2 points, any random xn and xn plus m, and distance between them. Now this is less than or equal to by triangle inequality. This basically, this is another, in between. So we just look at all between xn and xn plus m. You can do m addition. So that's what we have done here. So by triangle inequality, these are all consecutive points, and sum of them is bigger than this. And now, just now in the previous slide, we have seen this is less than or equal to alpha power n times and distance of x0, x1. So similarly, you have alpha n here, from alpha n n plus 1 from here, and so on. And here alpha n plus m minus 1. Okay. And now this is precisely a geometric progression, right? Geometric progression. So this the sum of these finite things is precisely is known, but so we are just going to use inequality. So this sum is smaller than the infinite sum, which actually converges to this. This is what you will have. So this is less than or equal to alpha n over 1 minus alpha dx0 xn. But since it's a contraction map, alpha is strictly less than 1. Therefore, for any given epsilon, one can choose an n naught such that alpha n over 1 minus alpha n over 1 minus alpha dxn is less than epsilon for all n bigger than or equal to n. Okay. Okay. So which means that for all n greater than or equal to n naught, we have shown that this dxn xn minus 1 is less than or equal to this, which is less than epsilon for all n greater than or equal to n naught. Okay. So right, what we are saying here is that because by contraction alpha is strictly less than 1, it's a number less than 1, right? So I can find n here, power of n here, because everything else is fixed here. You see x0, x1, all these are fixed, right? Alpha, everything is fixed, so we can choose a n here such that this can be made smaller than whatever epsilon that we choose. So that way we get this less than epsilon. So that way we have shown that it's a Cauchy sequence, and because the metric space that we started with was a complete metric space, this Cauchy sequence has to converge, which means there is a limit x in the metric space itself, right? Now since the map, every contraction map is continuous, I give it as an exercise, right? Contraction maps is Lipschitz is continuous. It's a continuous map, so it preserves the convergence of the sequence. So f of xn will converge to f of x, since xn converges to x in x, right? So f of x is the limit of f of xn, but f of xn, the way we have defined the sequence, is precisely xn plus 1. So limit of xn plus 1, which is same as limit of xn, which is x, which means f of x is equal to x. So which means that x is a fixed point of f. So you see we started with a random point x0, right? And just by looking at the image of the point, recursively looking at the image of the point and so on, we had constructed a sequence, and that sequence leads us to the fixed point. Okay. In fact, just the right time to mention here is that if you have come across Picard's iteration and so on, it is picked up from this thing. We are going to see proof in the next lecture probably, but then we will not see the Picard's iteration proof. It is usually done at a very elementary OD course. Um, so that is actually coming from this kind of an algorithm, right? So when you want to find the solution of the ODE, you actually construct an approximate sequence, I mean, sequence of solutions which will converge to the original solution, and this is very much useful in computing the solution and so on in so numerics and other stuff. Okay, so this was an idea of Picard to do that, but this is a more general. Here we are doing in a very general metric space. We are saying how to obtain a fixed point. Anyway, we have obtained a fixed point. Now what remains is uniqueness. So uniqueness will follow, because if there are 2 points x and y such that they are fixed points of f, then the distance between x and y is distance between f of x and f of y, because they are fixed points. So x is same as f of x. Now by contraction, this is less than or equal to alpha dxy. But since alpha is less than 1, we should have that dxy distance between x and y should be 0, right? Because from here we get that yeah, if they are if dxy is non-zero, then you actually get alpha is bigger than or equal to 1, which is not the case since alpha is less than 1, which means dxy should be 0, which means that x and y should be same. So you actually have a unique fixed point uh, for the contraction map in a complete metric space. Okay. Okay, so as a remark, we just want to highlight that this is not true for the case when alpha is equal to 1, that is when f is non-expansive, right? In general, this is not true, right? For instance, if you take this map f of x plus plus x plus a, right, this will be a non-expansive map, and this does not admit a fixed point. Sorry. Yeah. Okay, so this is fine. So now a special case of this contraction mapping, and actually not special case, a little bit more generalized version of that is that a corollary to that theorem you can say, so if X is a complete metric space and F is a mapping such that now F power n is a contraction. Earlier we were saying F is a contraction. Now F is a mapping such that F power n is contraction. So in the previous case F power 1 was contraction. Here we are not given that F is contraction, but some power of F is contraction. Even in that case, you have a unique fixed point for F, not Fn. See, if Fn is a contraction, there is anyway fixed point for Fn. The theorem is telling you that if F is a map and F power n is contraction for some n, then still F has a fixed point. Okay? The proof is also quite simple. Let's just see, but bit bookkeeping and tricky. That's otherwise a very easy proof. So since Fn is a contraction by the previous theorem, there is a unique point, right, x star, which is a fixed point for Fn, right, because it's a contraction. So Fn x star is x star. So now what we see is, we look at f of x. So we want to show that f has a fixed point. So we look at f of x star. So when we look at f of x star, by since x star is a fixed point of Fn, x star can be replaced by Fn x star, which is Fn plus 1 x star, which is Fn power f of x star. Okay. Now this tells you that f of x star is a fixed point of f power n. Right? We already have x star as a fixed point of f power n. And if whenever x star is a fixed point of f power n, we have shown that f of x star is a fixed point of f power n, which means by the uniqueness of the fixed point, f of x star should be same as x star, right? Which means that f of x star is a fixed point of f of n, with the uniqueness f of x star is same as x star. Thus the fixed point of Fn is also the fixed point of f. So we have a fixed point for Fn, and the same point works as a fixed point for f as well. Now for uniqueness, if you have another point y star, fixed point of f, then Fn of y star is Fn minus 1 f of y star is equal to f of n minus 1 y star. Okay, so right, because anyway, what I am let me repeat. I just lost my attention there. So if y star is another fixed point of f, then we look at what is f of n y star. And now y star is a fixed point of f, which means that f of Fn of y star can be written as Fn minus 1 of f of y star, right? Now f of y star is a fixed point of f, so f of y star is same as y star, so it's Fn minus 1 of y star. So Fn of y star is Fn minus 1 y star. Similarly, the same argument can be repeated to say that Fn minus 1 y star is Fn minus 2 y star, and so on. Arguing this way, we can actually obtain that Fn of y star is f of y star, and Fn of y star is equal to y star, because y star is a fixed point of f. And now, right? Wait a second. What did I? So we have Fn of y star is equal to f of y star, and why am I repeating this? There's some mistake here. But no, what is that? Just give me a second. So what is that we wanted to prove? We wanted to prove that this was, we have proved that there is a fixed point, and what am I missing? So we want to show the uniqueness of the fixed point. So we want to show y star is same as y star is same as x star. So we have shown that f of n of y star recursively we can get it as Fn minus 1 Fn of y star as f of y star, and y star is a fixed point of y star is a fixed point of y star, which means that we have f of which means that they are same, right? We have proved that f of fn of y star is same as this, but then f1 has a unique fixed point. So what we have shown is that fn of y star is also y star, and but then there is a unique fixed point for f power n. So this x star should be same as y star. Yeah, sorry, I just lost it. Okay, so that way we have unique fixed point, right? And a very special case of this fixed point theorem is this Banach fixed point theorem, right? Which is just applying the contraction mapping theorem, fixed point theorem to the space of continuous functions, right? So in this case, it's a ball of radius r. So you have a closed interval I in r, and you fix a g, which is a continuous function. So here I have taken I to be the closed interval. Okay, so it's already closed, and you take a g and you fix a, you take an r and you look at the ball of radius r centered at g in ci in its metric, which is a uniform metric. So that ball is this all f such that which is in the distance radius r, right? So it's a ball of radius r centered at g in the space of continuous function, right? And if t is an operator from the ball to ball, which is a contraction operator, which means it satisfies this for all elements in the ball, then the t has a unique fixed point, right? So same as, so this just follows from the contraction mapping principle, right? Because the Ci is a Banach space and B is a closed subspace of the Banach space, so the restriction is a restrictive topology, right? So relative topology is also complete. So B is also a complete space. So you have the operator T from a complete metric space to a complete metric space, right? So by the contraction theorem, this result follows. So this is the Banach fixed point theorem, right? Which is actually a special case of the contraction mapping theorem, the simple contraction mapping theorem. Okay, so we have shown the situation where you can have a fixed point for an operator, and we started this lecture by reducing a kth order ODE to a first order system of ODE and saying that solving the first order system of ODE is same as finding the fixed point for a corresponding operator on the space of continuous functions. And we have given a condition here when can such a fixed point exist, right? In the next lecture we are going to use these fixed point results to actually give an existence and uniqueness of solution proof for the first order system of ODEs. Okay, then see you in the next lecture. Thanks a lot.